Everything you see in the night sky is a tiny fraction of reality. The stars, planets, and galaxies are just the visible 5%. The rest of the cosmos, a staggering 95%, is made of two invisible and mysterious components: dark matter and dark energy. These are the fundamental forces shaping the universe, yet they remain completely hidden from our direct sight. We are about to journey through 25 mind-blowing facts that will completely reshape your understanding of the cosmos. You will discover how we know this invisible universe exists and why it holds the ultimate keys to our cosmic fate. We will uncover why galaxies spin too fast to hold themselves together, and why the expansion of the universe is accelerating against all expectation. What do you believe is the most profound mystery waiting for us in the dark? Our entire visible universe is just a tiny fraction of what is actually there. Every star, every planet, every single thing you have ever seen or touched accounts for less than 5% of the cosmos. The rest is composed of two profound mysteries: dark matter and dark energy. Dark matter makes up about 27% of the universe, while dark energy is a staggering 68%. This means that over 95% of everything that exists is completely invisible to our eyes and our telescopes. It is a universe hidden in plain sight. Think of it like this: the glittering galaxies and shining stars we admire are merely the fleeting foam on the surface of an immense, dark, and uncharted ocean. We are only just beginning to understand the depths that lie beneath. The first clue to this hidden reality emerged nearly a century ago with a brilliant and troubled astronomer named Fritz Zwicky. Studying the distant Coma cluster, a vast collection of galaxies, Zwicky made a startling observation. The individual galaxies were whipping around the cluster's center at unimaginable speeds, millions of miles per hour. According to the well-understood laws of gravity, there was a huge problem. The combined gravitational pull from all the visible stars and gas in the cluster was far too weak to hold onto these runaway galaxies. They should have been flung out into the void of intergalactic space, scattering the cluster across the cosmos. Yet there they were, held firmly together by some unseen force. Zwicky concluded that there must be a tremendous amount of invisible matter providing the extra gravity, a cosmic glue. He called it Dunkel Materie, dark matter. This ghostly grip is what keeps entire galaxies from spinning themselves apart. Picture a child on a fast merry-go-round. If the ride spins too quickly, the child flies off. Now imagine that same child mysteriously held in place by invisible hands. That is the role dark matter plays on a cosmic scale. Its immense gravitational presence forms an unseen scaffold, a hidden skeleton that keeps galaxies and galaxy clusters intact against forces that should tear them to shreds. Without this mysterious anchor, our own Milky Way would be a very different and likely far more lonely place. Zwicky's invisible cosmic glue does far more than just hold individual galaxies together. It is the master architect of the entire visible universe. After the Big Bang, while the hot, bright soup of ordinary matter was still a chaotic blur, dark matter began to cool and clump together under its own gravity. It formed a vast, intricate skeleton, a network of immense filaments and dense knots that astronomers call the cosmic web. This dark framework is the hidden blueprint for everything we see. Ordinary matter, the atoms that make up stars and planets, was simply drawn along for the ride. Drawn by the irresistible gravitational pull of this invisible architecture, gas and dust flowed into the densest intersections of the web, piling up into the first protogalaxies and eventually igniting into the brilliant islands of light we now observe. Supercomputer simulations show this process in stunning detail, revealing a universe structured like a colossal spiderweb, with glittering galaxy clusters marking the nodes where the dark filaments intersect. Without this foundational scaffold, galaxies would be scattered randomly across the void with no grand design. The majestic cosmic structures we take for granted were not built by the stars themselves, but by the ghostly hand of dark matter sculpting the emptiness into a universe of breathtaking order. This ghostly cosmic skeleton is built from a substance that fundamentally ignores light. Dark matter does not emit, absorb, or reflect a single photon of electromagnetic radiation. It is utterly and completely transparent. Think of a perfectly clean window pane. You look right through it, unaware of its presence, only seeing the garden on the other side. Dark matter is like that, but for the entire universe. We are looking straight through it at the distant stars and galaxies beyond. This is the core reason our most powerful telescopes, from the Hubble to the James Webb, have never directly seen it. They are designed to collect light, and dark matter simply refuses to play that game. It is the ultimate cosmic introvert, existing alongside everything we see without ever making its presence known through sight or sound. So how can we possibly know it is there at all? We detect it by watching how it pushes and pulls the things we can see. Its immense gravity bends the very fabric of space-time, warping the path of light from distant galaxies in a phenomenon called gravitational lensing. It is like seeing the silhouette of an invisible giant by watching how it distorts the landscape behind it. We see galaxies moving in ways that defy the pull of visible matter alone, and we see the grand architecture of the cosmic web, a blueprint that could only have been drawn by an unseen hand. Everything we know about this mysterious substance comes not from seeing it, but from observing the profound shadow it casts upon the visible universe. But what exactly is this invisible cosmic material made of? Scientists have proposed several compelling candidates, with two leading the race. The first are known as WIMP, an acronym for Weakly Interacting Massive Particles. As their name suggests, these are hypothetical particles that are thought to be heavy, perhaps dozens or even hundreds of times more massive than a proton. Their key trait is that they ignore almost everything. They do not interact with light or the strong nuclear force that binds atomic nuclei. Their only significant interactions would be through gravity and the weak nuclear force, the same force responsible for certain types of radioactive decay. This aloof nature perfectly matches the ghostly behavior we observe. The second major candidate is the complete opposite in scale, the action. Theorized to solve a deep puzzle in particle physics concerning the symmetry of subatomic forces, actions are imagined to be incredibly light, trillions of times lighter than an electron. They would flood the universe in unimaginable numbers, a slow-moving, pervasive fog providing the necessary gravitational pull. The global hunt for these phantom particles is one of science's greatest adventures. To shield them from the constant cosmic noise at the surface, ultra-sensitive WIMP detectors are placed deep underground in abandoned mines or beneath mountains. They wait patiently for the once-in-a-lifetime event. The faint shudder that would signal a dark matter particle has finally collided with an atom of normal matter. Meanwhile, other experiments try to create dark matter from pure energy within the world's most powerful particle colliders, like the Large Hadron Collider. For decades, this search has been a roller coaster of excitement and frustration, with tantalizing hints that have all, so far, faded into nothing. The question remains, are we on the verge of a monumental discovery, or is the true nature of dark matter something even stranger and more elusive than we have ever imagined? Einstein's theory gave us a new way to see the invisible. He proposed that mass warps the very fabric of space and time, creating what we perceive as gravity. This warping does not just affect planets and stars, it bends the path of light itself. When light from a distant galaxy travels toward us, it must pass through this warped cosmic landscape. If its journey takes it near a massive cluster of galaxies, its path is curved, like a marble rolling across a stretched rubber sheet. The cluster acts as a gigantic natural lens. This phenomenon is called gravitational lensing, and it is our most powerful tool for mapping the dark matter we cannot see. we look for the telltale distortions in the shapes of galaxies far in the background. Their light is stretched and twisted into faint arcs, smears, and sometimes perfect circles of light known as Einstein rings. These are not tricks of the telescope, they are the ghostly signatures of dark matter's immense gravitational pull. By carefully measuring these cosmic mirages, astronomers can literally trace the outline of the invisible dark matter halo surrounding a galaxy cluster. They can create a map of the unseen. It is as if we are watching the silhouette of an invisible giant move through a field of tall grass, seeing only the way the grass bends and sways to mark its passage. Every distorted galaxy, every luminous ring is a data point, a clue that allows us to chart the distribution and quantity of the universe's hidden mass. This is how we know dark matter is not smoothly spread out, but is clumped into a vast, intricate cosmic web, its gravitational influence written in light across the sky. Perhaps the most dramatic proof for dark matter's existence comes from a cosmic crash site over 3 billion light-years away. Astronomers call it the Bullet Cluster, a system where two immense galaxy clusters have violently collided. This event created a perfect natural laboratory, revealing a stunning separation between what we see and what actually exerts gravity. When these clusters slammed together, their different components behaved in radically different ways. The vast clouds of hot, glowing gas, detectable only with X-ray telescopes, were slowed by a powerful drag force, much like two clouds of smoke colliding and mingling. This intergalactic plasma piled up in the center of the wreck, but when astronomers mapped the total mass of the system using gravitational lensing, tracing how the collision warped the light from more distant galaxies, they found the true bulk of the matter was not in the center. The primary source of gravity had sailed right through the collision and now resided in two distinct clumps on either side of the gaseous wreckage. This is the ultimate proof that most of the mass is something entirely separate from the visible, interacting gas. That something is dark matter because it does not interact with anything except through gravity. The dark matter halos of the two clusters pass through each other, and the intervening gas, almost without a whisper of resistance, emerging cleanly on the other side. This observation delivered a decisive blow to alternative theories that suggested we simply do not understand gravity on large scales. If that were the case, the gravitational pull would always be centered on the visible material, the glowing gas. But the lensing map shows the gravity is clearly divorced from the light, proving a massive, invisible, and collisionless substance is the true source. The ghost had not only been spotted, it had been caught on camera separating from the scene of the accident. For generations, cosmologists were certain of one thing: the universe was expanding, but that expansion was steadily slowing down. The mutual gravitational pull of all the matter in the cosmos, both visible and dark, was acting like a cosmic brake, gradually tiring the great explosion of the Big Bang. The ultimate fate of the universe seemed to be a simple question of whether there was enough gravity to eventually pull everything back together in a big crunch, or whether it would simply coast forever towards a cold, dark stillness. Then, in 1998, two independent teams of astronomers made a discovery so shocking it ripped up the old cosmic rulebook and earned them the Nobel Prize. They were both studying a specific kind of exploding star, a Type 1 supernova, which always explodes with the same intrinsic brightness. This makes them perfect cosmic mileposts or standard candles, allowing scientists to measure vast distances across the universe. By observing how much these supernovae had dimmed, they could calculate exactly how far away they were. By measuring how much their light was stretched or redshifted, they could determine how much the universe had expanded since the star exploded. They expected to see that the more distant supernova, whose light had been traveling for billions of years, showed signs of a universe that was expanding more quickly in the past, proof that the expansion was indeed slowing down. The data revealed the exact opposite. The distant supernovae were fainter than they should have been. The universe was not slowing down at all, it was speeding up. The expansion rate was accelerating, as if some mysterious, repulsive force was actively pushing galaxies apart, overwhelming the collective pull of gravity itself. This was not just a new discovery, it was a complete inversion of reality. The cosmos was not winding down, it was winding up, driven by an unknown engine we now call dark energy. This single observation forced a paradigm shift in our understanding of cosmic destiny, revealing that the universe is ruled not by a steady deceleration, but by a mysterious and potent acceleration whose source remains one of the greatest enigmas in all of science. This accelerating expansion is the most profound cosmic paradox. Imagine throwing a ball straight up into the air with all your might. You watch it climb, expecting gravity to slow its ascent, bring it to a momentary halt, and then pull it back down to Earth. Now picture that ball at the very peak of its flight, suddenly igniting a rocket engine and hurtling away from you at an ever-increasing speed forever. That is precisely what our universe is doing. The collective gravity of every galaxy, every star, and every ounce of dark matter should be pulling the cosmos back together, yet something far more powerful is flinging it apart. This something is dark energy, a force that causes the very fabric of space itself to stretch at an ever-increasing rate. It is not that galaxies are rocketing through space like shrapnel from an explosion. It is that the emptiness between them is actively growing, creating more distance with each passing moment. Think of the universe as a loaf of raisin bread rising in the oven. The raisins, which represent galaxies, are not moving much through the dough itself, but as the dough expands, every raisin gets farther away from every other raisin. Now imagine the yeast in that dough suddenly becoming supercharged, making the loaf expand faster and faster with no end in sight. That runaway expansion is the reality we inhabit, driven by the enigmatic pressure of dark energy. This relentless acceleration paints a startling picture of the far future. If it continues unchecked, distant galaxies will be pushed away so quickly that their light will no longer be able to reach us. The cosmic horizon will shrink, and the universe beyond our local group of galaxies will fade from view, vanishing into an impenetrable darkness. The night sky for any future civilizations will become empty and black, a lonely island in an expanding void. In an even more extreme scenario known as the Big Rip, the accelerating expansion could eventually overcome the forces that hold galaxies, solar systems, and even atoms themselves together. The fabric of space would stretch so violently that it would tear apart every structure, from the largest clusters to the very particles that make up our bodies, leaving behind a desolate and fragmented cosmos. This is the ultimate power of dark energy, a force that does not just fill empty space, but commands the destiny of everything within it. Einstein's own equations held the secret to cosmic acceleration long before we even knew it was real. In 1917, he applied his new theory of general relativity to the entire universe and encountered a problem. His calculations insisted that the universe should be either expanding or contracting, pulled by its own gravity into a dynamic state of change. Yet the scientific consensus of his time, based on limited observations, was that the universe was static and eternal, an unchanging island of stars. To force his brilliant equations to match this flawed assumption, Einstein introduced a fudge factor, a mathematical term he called the cosmological constant. This was a kind of repulsive energy, a universal anti-gravity that would perfectly balance the inward pull of matter, holding the cosmos in a steady, unchanging state. When Edwin Hubble later proved the universe was indeed expanding, Einstein saw no further need for his contrived fix. He famously renounced the cosmological constant, calling it his greatest blunder, and the idea was largely shelved for decades. The irony is almost beyond belief. The very discovery that made Einstein discard his constant, the expansion of the universe, has now revealed an acceleration that behaves exactly like it. Dark energy, the force driving galaxies apart, acts with the same uniform, space-filling character as the repulsive energy Einstein first scribbled onto his blackboard. His greatest blunder was not the idea itself, but his decision to abandon it. He had unknowingly predicted the dominant component of the universe nearly a century before we had the evidence to see it. What he introduced as a mathematical stopgap to preserve a static cosmos has turned out to be the dynamic engine of an accelerating one. It is a humbling lesson from history that even our most brilliant minds can hold a truth in their hands without recognizing it, simply because the world is not yet ready to see. The leading suspect for dark energy's identity comes from the seemingly emptiest place of all, the void between galaxies. This prime candidate is vacuum energy, the intrinsic energy of empty space itself. In the bizarre world of quantum mechanics, a perfect vacuum is not peaceful or still. Instead, it is a turbulent sea of activity, a foam of so-called virtual particles. Particle and antiparticle pairs spontaneously flicker into existence for an unimaginably brief moment, borrowing energy from the void before annihilating each other and vanishing back into nothingness. This continuous, frantic dance of creation and destruction should imbue every cubic centimeter of space with a certain energy, and according to Einstein's theory of relativity, energy has gravitational consequences. This vacuum energy would produce a repulsive force, a constant pressure that pushes space apart, behaving exactly like the cosmological constant. It is an elegant idea that dark energy is simply the hum of nothingness, the background static of reality itself. Yet this beautiful theory is shattered by a number, a calculation so catastrophically wrong it represents the greatest failure of theoretical physics. When physicists calculate how much repulsive force this quantum frenzy should generate, the answer is absurd. The predicted strength of this vacuum energy is 10 to the power of 120 times greater than the gentle acceleration we actually observe in our universe. That is a 1 followed by 120 zeros, a discrepancy so vast it is impossible to visualize. If the theoretical prediction were correct, the repulsive force would have been so immense that it would have blown the embryonic universe apart in the first fraction of a second, preventing any galaxy, star, or planet from ever forming. We would not be here to ponder it, so why is the cosmos so much quieter than the math demands? Why does the energy of the vacuum appear to be almost but not perfectly zero? This gap between prediction and observation is more than a simple error. It is a fundamental crisis, a screaming clue that there is a profound piece of reality we are completely missing. But what if Einstein's cosmological constant is not the final answer? Its unchanging nature offers one compelling explanation, yet another, even more exotic possibility exists, a dynamic and evolving force known as quintessence. Imagine a fifth fundamental force of nature, a new kind of field that permeates all of space. Unlike the static vacuum energy of the cosmological constant, quintessence is a theoretical energy field that can change in strength and density over time. It is not a constant, but a fluid, a cosmic essence that can either accelerate the expansion of the universe more gently in some eras or more violently in others. The name itself, quintessence, is borrowed from ancient philosophy, where it referred to a fifth element beyond earth, air, fire, and water, a pure substance that made up the heavenly bodies. In modern cosmology, it represents a similarly fundamental ingredient, a dynamic dark energy whose repulsive push could be slowly fading away or perhaps even growing stronger. This idea opens up a universe of possibilities far more complex than a simple, steady acceleration. The central question driving astronomers today is a deceptively simple one. Has the strength of dark energy always been the same? To find the answer, they are building the most precise maps of the cosmos ever conceived. By observing billions of galaxies and thousands of distant supernovae, instruments like the Dark Energy Survey and the upcoming Vera C. Rubin Observatory are essentially constructing a cosmic movie of the universe's expansion. They are looking for tiny deviations in how quickly the universe was growing at different epochs, from its youth to its middle age and into the present day. If the expansion history shows even a slight wobble, a hint that the repulsive force was different 8 billion years ago than it is now, it would be definitive proof that dark energy is not a cosmological constant, but the dynamic force of quintessence. Such a discovery would force us to rewrite the standard model of cosmology, transforming our understanding of the fundamental forces that have shaped and will ultimately dictate the fate of everything. The history of our cosmos is written in the tension between two invisible giants. For billions of years, dark matter held the upper hand. Its relentless gravitational pull worked like a cosmic magnet, drawing ordinary matter into the filaments and nodes of the great cosmic web, sculpting the first galaxies and the magnificent clusters we see today. The universe was a place of construction, of gravity patiently gathering the raw materials for stars and planets. But this was only the first act. As the cosmos continued to expand, the density of matter, both dark and normal, began to thin out. The gravitational glue that had been binding everything together was slowly weakening, diluted across an ever-growing void. Then, around 5 billion years ago, a fundamental shift occurred. The scales tipped. Dark matter's inward pull was finally overcome by the outward push of dark energy. We now live in the dark energy-dominated era, a chapter in cosmic history defined by this repulsive force. The great tug of war is over and dark energy is winning. The consequence is an accelerating expansion that is actively reshaping the future of the cosmos. Galaxies are not just drifting apart, they are being pushed apart by the very fabric of space itself. This transition from a gravity-driven universe to one ruled by anti-gravity is the single most important event since the Big Bang for determining our ultimate fate. It is the reason our distant future looks so vastly different from our past, a future where the lights of other galaxies will one day fade from view, leaving our local celestial neighborhood isolated in an endless, expanding dark. To uncover the universe's deepest ingredients, we must look back to its very first light. This ancient glow is the cosmic microwave background, the fading ember of the Big Bang itself. For 13.8 billion years, this radiation has traveled across the cosmos, carrying an imprint of the infant universe. It is a snapshot of a time when everything was a searing hot plasma, a roiling sea of particles and light. As the universe expanded and cooled, atoms formed and light was finally set free, streaming across space. Today, that primordial light has cooled to just a few degrees above absolute zero, a faint microwave whisper that fills every part of the sky. It is the oldest fossil we can possibly observe, and etched into its subtle warmth is the complete blueprint for everything that would follow, including the nature of dark matter and dark energy. By creating incredibly precise maps of this background, satellites like Planck have revealed that it is not perfectly uniform. Instead, it is a tapestry of minuscule temperature variations, tiny patches that are ever so slightly warmer or colder than the average. These tiny fluctuations are the seeds of all cosmic structure. The slightly denser regions where dark matter was already beginning to clump held more energy, appearing as warm spots. The less dense regions were cooler. The precise size and distribution of these hot and cold spots are not random. They are a frozen record of the universe's composition and geometry at that precise moment in time. By analyzing these intricate patterns with phenomenal precision, cosmologists can perform what is essentially a cosmic accounting. They can measure the total density of the universe and break it down into its fundamental components. The results give us our most precise cosmic recipe. The patterns tell us that ordinary matter, the atoms that build stars and planets, makes up just about 5% of the total. Dark matter, the invisible scaffolding, accounts for roughly 27%. and the remaining 68% is the enigmatic dark energy driving the accelerated expansion. This ancient afterglow does not just hint at the existence of these mysterious components, it measures them with a staggering degree of accuracy, confirming that the universe we see is truly just the tip of a vast dark iceberg. Dark matter's invisible hand was not just a sculptor of existing galaxies, it was the essential midwife for their very birth. In the fiery aftermath of the Big Bang, the universe was a searing, opaque fog of particles and energy. Ordinary matter, the protons and electrons that would one day become us, was trapped in a violent dance with light. Radiation was so intense that it blasted atoms apart, preventing them from ever clumping together. A cloud of hot gas wants to expand, not contract. If gravity tried to pull on a pocket of this primordial hydrogen, the immense radiation pressure would simply push it back apart, like trying to build a sandcastle in a hurricane. For stars and galaxies to form, something had to create a calm harbor within this chaos. That something was dark matter. Because dark matter ignores light and radiation entirely, it was completely unaffected by the cosmic turmoil. This allowed it to start clumping together through gravity almost immediately, long before ordinary matter could. These clumps grew over millions of years, forming vast spherical halos of pure, invisible mass. These dark matter halos became the universe's first structures, the gravitational anchors for everything to come. Once these wells of gravity were established, they began to pull in the frantic ordinary matter. The hydrogen and helium gas would fall into these deep gravitational pits, and there, finally shielded from the worst of the radiation, it could begin to cool. As it cooled, the gas could condense, swirling into dense disks at the centers of these dark halos. Only then, within these protected nurseries, could the gas collapse further under its own weight, igniting into the very first stars and assembling the earliest faint galaxies. Without these pre-existing dark matter foundations, ordinary matter would have remained a diffuse, formless cloud forever. The night sky would be utterly black, a silent and endless sea of dark gas with no islands of light. Every galaxy we see, including our own Milky Way, exists only because it formed at the heart of a much larger, invisible halo of dark matter. We are literally living in the shadow of a ghost. Our own cosmic neighborhood holds a ghostly mystery that challenges the very foundations of our dark matter theory. Sophisticated computer simulations, which trace the growth of the cosmic web from the Big Bang to today, paint a very specific picture of what should surround a galaxy like our Milky Way. They predict that thousands of small, dense clumps of dark matter should be orbiting our galactic home, the leftover building blocks from the universe's construction phase. Each of these dark matter halos should have been massive enough to pull in gas and ignite stars, meaning our sky should be filled with the faint glow of thousands of tiny satellite galaxies dancing around the Milky Way. The reality, however, is starkly different. When astronomers scan the heavens, they find only a few dozen of these dwarf galaxies. The vast majority of predicted satellites are simply missing. This glaring mismatch between theoretical prediction and actual observation is known as the missing satellite problem, and it remains one of the most persistent cracks in our understanding of dark matter's role. It forces us to ask a difficult question: are the simulations wrong, or are we just not seeing the full picture? One compelling solution suggests that the dark matter clumps are indeed there, just as the models predict, but they are simply too dark to see. Perhaps the vast majority of these small halos failed to attract or hold onto enough gas to form a significant number of stars. They could be entirely dark, invisible galaxies composed of nothing but pure dark matter, their presence only detectable through subtle gravitational tugs on the visible objects around them. Another possibility strikes at the heart of galaxy formation itself. Maybe our understanding of how stars ignite within these small halos is incomplete. The intense radiation from the first stars or from neighboring galaxies could have blown away the fragile gas in these small clumps, sterilizing them before they could truly become galaxies. This would leave behind a swarm of dark matter ghosts, real and massive, but utterly devoid of the light we use to find them. The missing satellite problem is not a failure of the dark matter model, but a vital clue. It shows us that the story of dark matter is far from complete, and that its intricate dance with ordinary matter is more complex and fascinating than we ever imagined. But what if we have been looking at the puzzle from the wrong angle entirely? What if the invisible giant does not exist, and the problem is not with the universe, but with our understanding of gravity itself? This is the radical proposition of a theory known as modified Newtonian dynamics, or MND. It dares to suggest that Isaac Newton and Albert Einstein did not have the final word, at least not on the grandest scales. MND proposes that gravity does not behave exactly as we think it does in environments of extremely weak acceleration, like the sparse outer regions of galaxies. In these lonely outskirts, the gravitational pull from the central mass becomes almost imperceptibly faint. According to MND, under these specific conditions, gravity gains a subtle extra kick. This small modification to the laws of physics is enough to explain why stars on the edges of galaxies orbit at such high speeds, all without needing a single ounce of invisible dark matter. It is a beautifully simple idea that the solution is not a missing substance, but a missing piece in our most fundamental theory. For certain galactic phenomena, MND works remarkably well, often predicting rotation curves with stunning accuracy where standard gravity fails. Yet for all its elegance, this theory faces its own monumental challenges. The most damning evidence comes from cosmic crash sites like the Bullet Cluster. Remember, the gravitational lensing map showed the bulk of the mass was separate from the visible matter, having sailed right through the collision. MND struggles profoundly with this because its modified gravity is still tied to the location of the visible stars and gas. It cannot easily explain how the primary source of gravity could become completely divorced from the material we see. Furthermore, the intricate patterns in the cosmic microwave background, the universe's baby picture, are a perfect match for a cosmos built on a foundation of dark matter. Reproducing this detailed blueprint with a modified gravity theory alone has proven incredibly difficult. The existence of dark matter is woven into the very fabric of our standard model of cosmology, and MND has not yet been able to replicate its sweeping success. So we are left with a deep and unresolved conflict. Is the cosmos filled with a mysterious, invisible particle that shapes everything? Or are our laws of gravity, which have served us so well for centuries, finally showing their limits on the universal stage? The silence underground is profound. Far beneath mountains or deep within abandoned mines, scientists have built the quietest rooms in the world. These are the cathedrals of modern physics, places like Snowlab in Canada, accessed by descending a mine shaft 2 kilometers deep, or the Gran Sasso Laboratory in Italy, nestled under a massive rock shield. Their sole purpose is to listen for a whisper from the dark. Here, shielded from the constant barrage of cosmic rays and natural radioactivity that bombards the surface, researchers wait for an event of unimaginable rarity, the direct collision between a dark matter particle and an atom of normal matter. The entire experiment is a masterpiece of patience and precision. At its heart is a chamber filled with an ultra-pure material, often liquid xenon or a crystal of pure silicon, kept at extreme temperatures. This is the target, a vast, silent net cast into the cosmic river. Billions of dark matter particles are thought to be streaming through this room and through your body every second. But because they interact so weakly, they pass through everything, the rock, the walls, the scientists, and the detector itself, without leaving a trace. The hope is that once in a great while, one will strike the nucleus of a xenon or silicon atom head-on. The impact would be incredibly faint, a tiny flash of light, a minute amount of heat, or a small electrical charge, a signature a billion times smaller than what any other known particle would produce. To spot this infinitesimal signal, the detector must be kept in a state of perfect quiet. It is encased within layers of shielding, lead to block gamma rays, copper to stop other impurities, and often a tank of pure water to absorb any remaining neutrons. The entire apparatus is a fortress against noise, designed to eliminate every possible false alarm. For decades, these experiments have been running, their sensitivity growing with each new generation. They have pushed deeper and deeper into the territory where dark matter particles should be hiding, scanning vast swaths of possible masses and interaction strengths. And yet, the definitive signal has not come. The detectors remain silent. This great silence is both a mystery and a catalyst. Each null result is not a failure, but a map that tells us where not to look, forcing us to refine our theories and build ever more sensitive machines. The hunt continues in the profound quiet, a testament to our relentless drive to finally touch the invisible. While our deepest laboratories listen in silence, other scientists are scanning the heavens for the echoes of a phantom battle. This is the search for indirect detection, a hunt not for dark matter itself, but for the fallout from its self-destruction. The theory is compelling. If dark matter is indeed made of particles, then it is possible that when two of them collide, they could annihilate each other in a flash of pure energy, converting their mass into a cascade of other particles we can actually see. It is a cosmic game of Clue. We cannot find the criminal, but we can look for the smoking gun. The most sought-after signature is a burst of high-energy gamma rays, the most powerful form of light. Telescopes like the Fermi Gamma Ray Space Telescope constantly scan the entire sky, mapping this gamma ray light. Scientists then look for places where this light appears in an unexpected, unexplained excess. The most promising hunting grounds are the places where dark matter should be most densely packed, the very heart of our own Milky Way galaxy or the centers of nearby dwarf galaxies, which are believed to be heavily dominated by dark matter halos. In these crowded regions, the chances of dark matter particles colliding and annihilating should be highest. Imagine a vast, dark cloud filled with fireflies that are normally invisible. But if two fireflies touch, they explode in a brilliant flash. You cannot see the cloud itself, but if you stare at it long enough and see a mysterious, persistent glow of flashes coming from its center, you can deduce the cloud is there and teeming with life. That is the principle behind this search. Researchers have also looked for other exotic signals, like unusual patterns in cosmic rays, which are high-energy particles racing through space, or even for faint neutrinos emanating from the sun. The idea is that as the sun moves through the galaxy, its gravity could trap a stream of dark matter particles in its core. If those particles then annihilate, they could produce neutrinos that stream out, carrying a message from the sun's dark, dense interior. For years, there have been tantalizing hints, especially from the galactic center, where Fermi has detected a faint, diffuse glow of gamma rays that is difficult to explain with known astrophysical processes. This galactic center excess has sparked immense excitement, but it remains a mystery. Is it the long-sought signal of dark matter annihilation, or is it simply a population of pulsars we have not yet resolved? The data is ambiguous, a whisper that could be a breakthrough or just cosmic background noise. This is the thrilling and frustrating nature of the hunt, where every potential signal must be scrutinized, every other explanation ruthlessly eliminated. The invisible universe continues to guard its secrets, revealing just enough to keep us searching. If you cannot find a ghost in the dark, you must try to create one in a flash of light. This is the daring logic behind the search for dark matter at the world's most powerful particle colliders. At the European Research Centre CERN, the Large Hadron Collider runs a breathtaking experiment. Inside a 17-mile circular tunnel buried deep beneath the French-Swiss border, physicists send tiny protons racing in opposite directions at over 99.9% the speed of light. They steer these beams into a head-on collision at 4 specific points around the ring, where cathedral-sized detectors stand ready. In these violent encounters, the immense energy of motion is transformed, condensing into new forms of matter. The goal is to recreate for a microscopic instant the searing conditions that existed a fraction of a second after the Big Bang. It is in this primordial furnace that dark matter particles might have first been forged, and by turning back the cosmic clock, we might be able to make them again. But this creates an obvious and profound problem. How do you detect something that is fundamentally invisible, that leaves no track and registers on no sensor? The answer is both brilliant and counterintuitive. You do not look for what is there, you look for what is not. After a collision, physicists perform a perfect accounting of all the energy and momentum carried into the event by the two protons. They meticulously catalog every single particle that comes flying out of the wreckage, measuring their paths and energies. In a perfect world, the energy going in should exactly equal the energy coming out. But if dark matter is created, the ledger will not balance. These phantom particles would carry away a significant amount of energy and momentum without leaving a single trace, escaping the detector completely unseen. The signature of their birth would be a glaring imbalance, a clear case of missing energy. Imagine two cars crashing in a sealed, white room covered in sensors. After the impact, you add up the energy from every piece of flying debris, every spark, every sound wave. If your calculations show that a large chunk of energy is simply gone, you can deduce that something invisible, perhaps a ghostly object, was thrown from the crash and passed straight through the walls. That missing energy is your only clue. This is the silent testimony physicists are searching for in the unimaginable chaos of a particle collision. So far, the books have balanced, with no definitive missing energy signal pointing to dark matter. Yet every collision is a new roll of the dice, a new chance to catch the invisible universe in the act of creation. All these threads of evidence weave together into a single, magnificent tapestry known as the Lambda CDM model, our current standard model of the entire cosmos. Its name is a compact code for the universe's fundamental ingredients. Lambda represents the cosmological constant, Einstein's once rejected idea that now defines our understanding of dark energy, the force accelerating the expansion of space. CDM stands for cold dark matter, referring to the concept that dark matter particles move slowly compared to the speed of light, a crucial detail that allowed them to clump together efficiently and form the cosmic web. This model is not just a vague sketch, it is a precise cosmic recipe, a set of instructions that, when plugged into the laws of physics, successfully builds a universe that looks exactly like our own. The numbers are now iconic. The universe is about 5% ordinary matter, the atoms that make up every star, planet, and person. It is 27% dark matter, the invisible scaffolding that gives the cosmos its structure. And it is a dominant 68% dark energy, the mysterious pressure stretching the fabric of space itself. This single, elegant formula manages to explain an astonishingly diverse menu of cosmic phenomena. It perfectly predicts the intricate speckled pattern of the cosmic microwave background, the universe's baby picture. It accounts for the accelerating expansion we see in distant supernova. It replicates the vast, web-like distribution of galaxies observed in sky surveys and explains how the first stars and galaxies could form so quickly after the Big Bang. This model is the crowning achievement of modern cosmology, a unified picture that fits nearly everything we see. Yet its greatest irony is that this triumphant model is built upon profound ignorance. We have named the pieces and measured their effects with stunning precision, but we still have no idea what dark matter and dark energy actually are. We are like master chefs who can follow a recipe to create a perfect, complex dish, yet we have never actually seen or tasted the two main ingredients that give it its essential flavor and form. The Lambda CDM model is not the final answer. It is our best map of a territory still largely unexplored, a guide that points directly toward the deepest mysteries waiting to be solved. This precise balance between dark matter and dark energy feels less like a cosmic accident and more like a carefully set dial. We exist in a very special window of time when both forces are potent enough to be roughly comparable in their influence on the cosmos. This is the cosmic coincidence problem, and it is deeply unsettling to physicists. Why now, for billions of years, dark matter's gravity dominated, allowing galaxies to form and life to eventually emerge? For the next billions of years, dark energy will dominate completely, pushing the cosmos into an ever-accelerating expansion. We happen to live in the brief sliver of cosmic history where the two are locked in a temporary stalemate, their energy densities within an order of magnitude of each other. If the value of dark energy were just slightly stronger by a factor of 10 or so, its repulsive push would have overwhelmed gravity in the universe's infancy. The cosmic web would never have formed, galaxies would never have coalesced, the universe would have been blown apart into a thin, featureless haze before the first star could ever ignite. Conversely, if dark energy were significantly weaker, gravity would have remained the undisputed master. The expansion of the universe might have slowed to a halt and reversed, collapsing everything back into a superheated singularity in a big crunch long before complex life could evolve. Our existence seems to hinge on this knife-edge balance. This leads to a profound philosophical question known as the anthropic principle. It suggests that the fundamental constants of our universe appear fine-tuned for life because if they were not, we would not be here to observe them. We are not just passive inhabitants of the cosmos. Our very presence is a data point that tells us something about the universe's allowable parameters. We are living proof that the dark energy density had to be small enough to allow for galaxy formation, but large enough to prevent a catastrophic collapse. It is a thought that connects our humble existence on a tiny planet directly to the largest scale forces governing all of reality. Does this mean the universe was somehow designed for life, or are we simply the lucky winners in a cosmic lottery with an almost infinite number of tickets, a multiverse where every possible value for dark energy is realized somewhere, and we naturally find ourselves in one of the rare universes that permits our existence? The silence of the cosmos offers no easy answer, only the staggering implication that the darkest secrets of the universe are intimately linked to the light of consciousness. The final chapter of our universe is written in the language of dark energy, and we are only now learning to read its opening lines. Depending on the true nature of this mysterious force, our cosmos faces one of three possible destinies, each more dramatic than the last. The most widely accepted forecast is known as the heat death or the big freeze. In this scenario, dark energy remains a constant, gentle pressure, much like Einstein's cosmological constant. The expansion of space continues to accelerate at its current, steady rate. Galaxies beyond our local group will be pushed away faster and faster until they cross a cosmological horizon, their light forever too stretched and faint to ever reach us. One by one, the lights in the sky will wink out. Within the surviving galaxies, star formation will slowly grind to a halt as the last reserves of interstellar gas are exhausted. Existing stars will burn through their fuel and die, leaving behind cold, dark remnants, black holes, neutron stars, and cooling white dwarfs. Even these final embers will not last. Over trillions upon trillions of years, black holes will slowly evaporate through a quantum process known as Hawking radiation, and protons themselves may decay. The universe will become a vast, nearly perfect vacuum, an eternally expanding sea of darkness at a temperature barely a fraction of a degree above absolute zero. It is a quiet, slow, and profoundly lonely end. But what if dark energy is not constant? If it is something like quintessence, a dynamic force that grows stronger over time, the end will be far more violent, a cosmic apocalypse known as the Big Rip. In this terrifying finale, the repulsive force of dark energy would intensify, overwhelming every force that holds the universe together. First, the acceleration would shred the cosmic web, tearing galaxy clusters apart. Then, the gravitational glue holding individual galaxies together would fail, sending stars flying into the void. As the force grows still stronger, it would attack solar systems, pulling planets from their stars. In the final moments, the stretching of space would become so violent that it would overcome the electromagnetic force holding atoms together. Every molecule, every atom, every atomic nucleus would be violently torn asunder. The very fabric of space-time would be ripped apart in a final, singular moment of destruction, leaving behind a fragmented, meaningless chaos. There remains a third, more speculative possibility, a dramatic reversal of fortune called the Big Crunch. This was the expected fate before the discovery of dark energy. It requires that the repulsive force of dark energy somehow fades away or even becomes attractive. If that were to happen, the expansion of the universe would slow, halt, and then reverse. Galaxies would begin rushing back toward each other, their collective blue shift growing as space itself contracts. The temperature of the cosmos would rise as everything is crammed into a smaller and smaller volume. The sky would glow hotter and hotter, first with infrared, then with visible light, and finally with deadly X-rays and gamma rays. The universe would end as it began, collapsing back into a singularity of infinite density and heat, a superheated fireball that might, in theory, set the stage for a new Big Bang and another cycle of creation. The key that unlocks which of these destinies is ours lies in the unknown nature of dark energy itself. Its unchanging strength condemns us to a cold, dark eternity. Its growing power promises a violent end. Its potential decay offers a cosmic rebirth. The ultimate fate of every star, every planet, and every atom depends entirely on the secret we are still trying to uncover. What if the entire cosmic story we have just told is built on a fundamental mistake? Our entire framework for understanding the universe rests upon two colossal assumptions: that dark matter and dark energy are real, physical things. But what if they are not? What if they are merely placeholders, mathematical ghosts summoned to explain observations that break our current laws of physics? This is not a fringe idea, it is a sobering possibility at the very heart of modern cosmology. We invented dark matter to explain why galaxies hold together despite spinning too fast. We conjured dark energy to explain why the universe's expansion is accelerating against all expectation. In both cases, we observed a gravitational anomaly, a behavior of the cosmos that did not match the predictions of Einstein's theory of general relativity or Newton's laws. Our solution was to propose that the universe is filled with vast amounts of invisible stuff and a mysterious repulsive force. But another path exists, one that questions not the contents of the universe, but the very rulebook of gravity itself. The problem is a deep schism in physics. General relativity, our theory of gravity, masterfully describes the cosmos on large scales, from orbiting planets to the expansion of space. Quantum mechanics, with equal brilliance, governs the bizarre world of the very small, the behavior of atoms and particles. The two theories are wildly successful in their own domains, but they are fundamentally incompatible with each other. They speak different mathematical languages and offer contradictory descriptions of reality. This tells us that our current understanding is incomplete. We are missing a unified theory, a theory of quantum gravity that seamlessly blends the cosmic and the quantum. It is possible that within this deeper, more complete theory, the phenomena we attribute to dark matter and dark energy would emerge naturally, not as substances, but as consequences of gravity behaving in new ways on the largest scales. The gravitational anomalies we see could be the first cracks in our current models, hints that gravity weakens or strengthens differently than we think in the near vacuum of interstellar space or over cosmic distances. Perhaps we are like cartographers trying to map the entire world with a chart that is only accurate for a single continent. The distortions we keep finding at the edge of the map are not evidence of invisible lands, but proof that our map itself is flawed. This perspective does not invalidate the incredible work of cosmologists, it elevates it. The true nature of science is not to carve answers in stone, but to remain perpetually open to revision. The names dark matter and dark energy are not declarations of truth, they are questions written in the sky. They represent our current best guess, a working hypothesis that is constantly being tested, probed, and challenged. The greatest discovery may not be the detection of a new particle, but the realization that our most fundamental laws require a revolution, one that will once again reshape our place in the cosmos. The silence will not last forever. A new generation of eyes is turning toward the sky, armed with technology that will transform our shadowy glimpses of the dark universe into a high-definition map. The next decade promises a revolution driven by observatories and experiments of almost unimaginable scale and sensitivity. In the Chilean Andes, the Vera Sea. Rubin Observatory is preparing for a monumental task. Its mission is to conduct a 10-year-long cinematic survey of the entire southern sky, a project that will capture the cosmos in motion like never before. Using the world's largest digital camera, it will photograph the entire visible sky every few nights, creating a time-lapse of the universe that will catalog billions of galaxies and detect millions of distant supernovae. This incredible volume of data will allow scientists to perform two crucial tests on dark energy. The first is by observing weak gravitational lensing on a colossal scale. By tracking how the light from countless distant galaxies is subtly distorted as it passes through the cosmic web of dark matter, astronomers will trace the invisible architecture of the universe with unprecedented precision. The second test comes from those supernovae. By finding thousands more of these standard candles, the observatory will measure the expansion history of the universe with a finer brush, looking for the tiniest wobbles that could reveal if dark energy is a constant or a dynamic force like quintessence. This is not a single snapshot, but a living, breathing movie of cosmic evolution. Joining this ground-based effort are two powerful space telescopes designed to see the dark. The European Space Agency's Euclid telescope is already on its way. Its goal to construct the largest and most accurate three-dimensional map of the universe ever made. It will peer deep into cosmic history, measuring the shapes and redshifts of over 1 billion galaxies to see how the tug of war between dark matter's gravity and dark energy's repulsion has shaped the cosmos over 10 billion years. Soon, it will be joined by NASA's and Nancy Grace Roman Space Telescope, a sister to the Hubble, but with a field of view 100 times larger. Roman will combine the power of a wide-area survey with the sharp vision of a space-based observatory, hunting for the faintest signatures of dark energy and scanning the galaxy for rogue planets and distant supernovae. Meanwhile, deep underground, the hunt for dark matter particles is entering a new phase. Next-generation detectors like LUX Zeppelin and its successors are scaling up, using ever larger vats of liquid xenon to increase the chance of that once-in-a-lifetime collision. These experiments are becoming so sensitive that they are beginning to probe regions of parameter space where many popular dark matter candidates are predicted to hide. If WIMP are there, these new machines are our best hope of finally feeling their ghostly touch. We stand at the threshold of a new era of discovery. For the first time, we are not just building instruments to answer our current questions, we are building them to reveal questions we have not yet even learned to ask. The true nature of the cosmos's dark side has remained hidden for all of human history, but the tools to finally bring it into the light are now within our grasp. The greatest chapters in our story of the universe are yet to be written. Our journey through the dark cosmos reveals a universe far stranger than we ever dreamed. We have navigated the ghostly grip of dark matter holding galaxies together, witnessed the repulsive force of dark energy tearing the cosmos apart, and stood in awe of a reality where 95% of everything is a complete and utter mystery. This is not the end of the story. It is the very beginning of the greatest detective story in all of science. Each unanswered question, from the identity of WIMP and actions to the true nature of the cosmological constant, is a beacon guiding us toward a deeper truth. This quest pushes the limits of our technology and our imagination, from laboratories buried deep underground to telescopes scanning the void. It reminds us that the universe is not only stranger than we suppose, but stranger than we can suppose. So the next time you find yourself under a clear night sky, look up, see the glittering pinpricks of light, the familiar constellations, and remember this: you are not just looking at stars. You are gazing at the visible 5%, the fleeting glitter on the surface of a deep, dark, and magnificent ocean whose currents and creatures remain almost entirely hidden from view. The greatest exploration in human history is happening right now, and it is an exploration of the invisible. Which of these 25 facts reshaped your understanding of the cosmos the most? Let us know in the comments, and subscribe to continue unraveling the deepest mysteries of the universe together.